Now, network monitoring has been around for a lot of time, probably ever since the first networks were invented. Just like with any system, just like with any electronic device, we tend to want to be able to monitor if everything is going okay. We want to receive warnings, we want to be alerted when something goes wrong, when something fails. And this type of monitoring is tremendously useful, especially in larger networks. Over time, this monitoring has extended to security monitoring as well. So we're not just concerned about how is the network doing, if it's working well, if you don't have any failed devices, but we're also starting to look at the network traffic. How is the network utilized? Who uses it? Who attempts to access it? What type of traffic are they generating? And if we try to gather all this type of information and we try to make sense of it, we try to correlate it with a smart enough device, we might be able to detect attempts at intrusion, or attacks that are about to happen or that have happened in the past, or proofs that we've been compromised or somebody in the network has been infected. And all that information is in there if you know where to look for, and also if you have the right tools to look for it. In general, the term intrusion detection refers to a system that is able to monitor whatever can be observed in a network. And in most cases, we're talking about two things that can be observed. First of all, we have network traffic, and then we have application events or logs generated by the operating systems, by the applications running on those OSs, and so on. So coming back here to our network focus, when talking about intrusion detection at the network level, we're going to call this one a network-based intrusion detection system, or NIDS. And we have many commercial solutions as well as open source ones that are able to perform this type of network-based intrusion detection. Of course, all the major security vendors are doing it. In many examples, you're going to see the IDS functionality built into the functionality of a larger firewall or a larger UTM device, especially for major vendors out there. But you also have solutions in the open source area, such as Snort, Suricata, or Zeek, or Bro. They're all available. Some of them also have commercial versions as well, but they also provide you with free versions that you can freely install and try and run in your own environment. Now, the way these intrusion detection systems work, by definition, is that they rely on a database of signatures. And those signatures are basically just a way to describe how a specific traffic pattern is supposed to look like in order to detect a specific type of attack or attempt at an intrusion. So we might be looking at a sequence of packets that looks in a certain way. We might be looking at a specific type of packet that doesn't play by the normal protocol rules that it belongs to, or a specific type of payload, or simply just a signature, a byte sequence that can be found in the packet payload that indicates the fact that the payload is malicious. And this behavior is very similar to what you're seeing in antivirus scanning or anti-malware scanning. We're simply looking for a sequence of bytes that indicates that, well, if we find the sequence of bytes in a specific executable file, it means that the file is infected with that specific virus that the sequence belongs to. Now, in intrusion detection, again, we're kind of doing the same thing, right? We're looking for patterns, but we're not just scanning individual packets. Sometimes we need to collect more packets in a sequence in order to determine if the behavior of the client that is generating those packets is abnormal, and if it's abnormal, does it indicate an attack pattern or not? So long story short, intrusion detection systems are strongly dependent on a database of signatures. Now, more advanced intrusion detection systems could also correlate this network information with log information. So we're seeing something fishy in the network by looking at the network traffic. Let's check the application logs that the traffic is going towards, for example. Let's see how that application reacts, and if we can see some abnormal logs being generated by the app as well. Now, correlating that information, the traffic and the logs, might tell us more about the actual attack, or might increase the confidence of the fact that we really have identified a valid attack signature. Not all solutions are able to do this, of course. Also, a very important distinction for intrusion detection system with an emphasis on detection is the fact that these systems are never able to block the malicious traffic once they identify it. It's just like the name says, it's just detection, it's not prevention. All right, so we're not stopping the traffic. We might be able to see an attack signature. We might be able to raise some alerts, generate some syslogs, but we're not going to be able to block that specific type of traffic. One positive side for this is that, well, if the device is not inside of the traffic path, then the attacker might not even be able to detect it. So most likely the IDS is going to work with a copy of the traffic just to analyze it, but it's not going to be able to stop the malicious traffic. And the attacker is not going to be able to detect the IDS device and might not even be able to compromise it if they intend to. In most situations, the IDS device doesn't even have a valid IP address within the network that they're monitoring, so it cannot be addressed, it cannot be compromised by communicating with it directly. Alright, so since we mentioned the fact that an IDS works with just a copy of the traffic, let's see how can we generate that copy of traffic, right? They're not within the traffic path, so we need to make a copy of the traffic and just send it in a separate channel, on a separate channel, to the IDS device for analysis. Now, one way of doing this is by enabling port mirroring, or SPAN. In Cisco speak, this is switch port analyzer, just a functionality on layer 2 or layer 3 switches that allow us to configure the switch, and we're basically telling it, well, whatever traffic you're seeing on ports, let's say 1, 2, and 3, make a copy of that traffic and forward it out of port number 8. And of course, we're assuming that on port number 8, there's an IDS device connected right there. So we're basically telling the switch to make a copy of all the interesting traffic and send it towards the IDS. And of course, you might be thinking here, well, what if the switch is overloaded? What if there's more traffic generated on those ports than the mirror port can actually support? Well, that's true, it might happen. So in cases when the switch is overloaded and there's too much traffic in the network, packets might be dropped, and also frames with errors might not be forwarded to the mirrored port either. So we might not be able to see 100% of all the traffic, but in most cases, it's going to be enough. And it's also one of the features that basically doesn't require you to install anything else in the network. It's just a functionality, just a configuration effort, just a couple of commands on a switch. Another method for duplicating traffic is by using a passive or an active. It's basically a layer 1 device called a TAP, a test access port. It's nothing else than a kind of like a T connector where the main cable goes from one end to the next, and there's a third cable that actually receives a copy of the entire traffic going through that segment of cable. The device is not a smart one, so it's not like a switch. It's not going to look at the destination frames and forward entire packets. It's simply going to duplicate the electrical or the optical signals that it sees on the wire, and it's going to make a complete and identical copy of those signals onto the third connection, which of course is ideally connected to the IDS device. Now, this type of approach is again completely undetectable. SPAN is not detectable either, right? And it also copies entire frames regardless if those frames contain errors or not. As we said, with port mirroring, well, the frames need to be correct in order to be copied. Well, with a TAP, the TAP doesn't care. It's basically just a signal repeater, and we can do this for both copper cables and so electrical signals, as well as fiber optic. So optical signals, the TAP will not care. We'll just blindly copy all the signals that it receives. And finally, the third method for monitoring traffic is by having the IDS device in the traffic path, but acting as a transparent device. Again, without an IP address, or basically becoming a layer 2 device that is part of the same VLAN that they're bridging, but they cannot be addressed on the network, they cannot be detected on the network, and if it's a true IDS device, then it's not going to be able to block the actual traffic that goes through it. Now, having the device placed inside of the traffic path opens us to the possibility of actually blocking the traffic, and that's going to be a different type of solution called intrusion prevention system, and we'll get there in just a moment. There's one more type of intrusion detection device or solution, and that is a software solution that can be installed directly on the workstations. So I'm not talking about a box that listens to network traffic on an entire segment, but we're talking here about a software solution, basically a program that runs on your endpoint machine, on your host machine, be it a laptop or a desktop. Now, this one is called host-based intrusion detection because it runs on the host, and it does have pretty much the same benefits or the same abilities as a network-based intrusion detection. So it's able to look at the network traffic going in and out of your network interface. It's able to look at the logs generated by the applications on your system, but since they are running as an application on your system, they can become even smarter because they might have access now to the actual process table. They might be looking at the kernel. You might be able to look at the memory to see what processes are running, when did they execute, who executed them, with what privileges. And they can also openly look at encrypted traffic. So if you are communicating over SSL with a website, well, a network-based intrusion detection might not be able to understand anything that's going back and forth because it's encrypted. But your host-based intrusion detection is located at the end of that encrypted tunnel. So it is able to see that unencrypted traffic before it even enters the encrypted tunnel and right after it leaves the encrypted tunnel. So it's able to actually watch the entire traffic flow in an unencrypted form. And again, since we have pretty much full permissions on the monitored host in order to be able to properly monitor the process table and the network connections and the network traffic, we could also have a look at the files on the disk. Why would you do that? Well, that's because monitoring the integrity of the files on the disk, especially the integrity of the operating system files, and being able to detect when that integrity fails, when a system file is being replaced with a malicious one, when a system file is becoming encrypted or it is replaced with a completely different version, that might be an indication of compromise. That might be an indication of the fact that you have been infected with malware. So solutions or functionality additional to host-based intrusion detection that monitor files on your system, especially operating system files, these are called file integrity monitoring solutions. And remember that we said that when we place the intrusion detection device in the traffic path, that device actually becomes able to also block the traffic that goes through it, which can make it an intrusion prevention system, right? So detection, just generate alerts or events. Intrusion prevention is about actually taking action or acting upon the detected intrusion. So what can such a device actually do whenever they're seeing something fishy going on inside of the network? Well, they could do something as simple as simply sending a TCP reset packet to the originator of the malicious connection. They could also have some more advanced functionality, especially if it's the same device that acts as a firewall. They might be dynamically able to generate a firewall rule to block similar traffic, like the one that was just detected as being part of an attempt for an attack or for a compromise. We could be choosing, if we're detecting something that looks like a denial of service attack, we could be choosing to limit the amount of bandwidth that is allocated to that specific type of traffic, kind of like policing that we're doing in quality of service. In any case, any type of action that the IPS device can take against the malicious traffic, we're going to call it active response. And depending on how complex the device is and how powerful the device is, you might actually choose to look not just at simple IPS or IDS signatures, but also look for malware signatures. That's going to require you to decode encrypted traffic. It's going to require you to identify potential protocols that might be carrying files, gather all those related packets that belong to the same TCP stream, to the same flow, assemble them into an executable file, store that in memory, attempt to scan it with an antivirus engine, and then determine if that flow was actually malicious or not. Now, this requires a lot of processing power. This is going to create some sort of delay in the network. So the users, they're going to see their download unable to finish, or the application responding slowly until the firewall, the UTM device, or the intrusion prevention system is actually able to scan those files against malware signatures. On a lighter approach, we could also just be looking at URLs, looking for malicious domains or domains associated with malware or with the command and control servers. We might be looking at URLs in order to categorize those URLs and figure out the reputation of that URL and decide whether we want the communication to that specific website to proceed or not. So regardless if the device is an IPS or an IDS, the detection methods are pretty much the same. Now, the difference is just in what the device is actually doing. Is it only alerting, or is it actually taking an active response approach to the traffic? But the detection part is pretty much the same, right? And when talking about detection, we are going to start with the basic type of detection. That is, we're just looking for signatures in the database, which of course means that we need to have an up-to-date database for the device to be able to detect the latest and the greatest attack. Now, this is basically one of the reasons why people choose to pay for commercial solutions, because databases maintained by a dedicated software or security vendor that deals with intrusion prevention, those databases are going to be much more often updated and kept up to date in order to mirror as best as possible the database of all the known attack patterns ever detected in the world. Now, with open source solutions, you're still going to have a pretty good level of protection, but you might not be able to detect an attack that was just identified 6 hours ago. Nevertheless, and regardless how up-to-date your database is, you're still limited by the attack patterns listed in that database. If an attack emerges and doesn't match anything in your database, it's still going to go through. Which leads us to a different approach, and that is a behavioral approach. So instead of looking at specific streams of bytes, specific headers, specific sequences of packets, let's look at the overall behavior of an application or of a protocol. Does it look like it's doing what it's supposed to do? Is it generating more packets than we're used to seeing? Is it generating more traffic? Is it generating an abnormal amount of control information as opposed to real transferred data? And we call this behavioral monitoring. Now, in order for behavioral monitoring to work, we need to have something to compare that behavior to and say, well, if it goes outside of the known ranges, then it looks like something's fishy. Well, that known range is supposed to be your baseline. So such a device or such a system is supposed to be trained first. You're supposed to just leave it inside of the network for, let's say, a week or two. Just let it figure out how does a normal Monday morning look like in your network when everybody comes into work and they start logging in and start updating their machines, or perhaps even their mobile phones on the company Wi-Fi. But nevertheless, you have to leave that intrusion prevention solution, learn what does your normal traffic look like when people start accessing internal applications, when people start accessing internet destinations, when people start communicating, sharing files between each other, when backups start to happen at midnight, perhaps, right? You have to let it learn so that in a couple of weeks, when something goes outside of the known range, where an application behaves the way it did not behave in the first training weeks, then it's going to be able to raise an alarm and perhaps indicate the fact that the application has been compromised, or that somebody is using it in order to elevate their privileges or just compromise your network. And as you can probably guess, this is one area where machine learning is going to provide a lot of benefit, given that you take the time and effort to educate, to teach the machine learning system what does your normal baseline look like. Now, of course, regardless how complex or how well tuned your solution is going to be, there will be false positives and there will be false negatives, which is why I always tell students, there's an old saying that I heard from someone in Cisco a long time ago, and they said that IPS without eyes is useless. So IPS without human eyes is useless. There's always going to be the need to have a human being right there evaluating and analyzing whether the alerts generated by the intrusion prevention or detection system are valid or not. Does it need more fine-tuning, or do we need to raise an alarm? So what devices can we actually find that implement this type of advanced functionality, be it detection or prevention? Well, unfortunately, this is the place where we're slowly stepping into the marketing area. That's because the devices that we're going to be listing here are not completely different devices. But over time, different naming conventions have emerged, different marketing names have been invented to make them sound cool, to make them sound different from what the other vendors were doing. So we're going to start with the next generation firewall. And we've had this type of next generation for about 12 or 15 years already. I've been hearing the next generation term in IT security for so long that I'm starting to wonder, are we still next generation? have we skipped the generation? Are we now in the next generation, or where does it stop? Where does it end? Where does the next generation begin, right? Now, unfortunately, marketing people don't really ask themselves these questions. So we're kind of stuck with this terminology for now, and we're going to keep calling it next generation until I don't know when. But regardless, a next generation firewall is basically just a layer 7 firewall. That's an application layer firewall, which is able to look at the application layer payload. So we're actually seeing the data being sent. We're not just looking at the packet headers. And it also has some sort of detection or prevention system built in. Okay, so we have an IPS or an IDS built in, which leads us back to the discussion that we had before. So we have an application layer firewall, which can be enriched with additional functionality. Now that we have access to the actual application payload, well, why not look for intrusion signatures? Why not look for malware signatures? Why not look for spam signatures, right? So depending on how complex the device is, if it at least has IPS functionality built in, we're going to call it a next generation firewall. And here's the funny part. If the next generation firewall has a bunch of other additional features on top of the IPS functionality, such as malware scanning, antivirus scanning, perhaps looking at the files and being able to implement some data loss prevention policies, it's able to look at the URLs and categorize them and analyze the reputation of the web pages and pretty much everything that we could possibly think of that we could be doing just by looking at the application data. Then we're going to call this a Unified Threat Management Device, a UTM device. Again, I don't think I need to repeat this, but the more complex a device becomes, the more stuff it needs to do in order to decide whether to allow a packet or not. The more resources, the more CPU intensive it's going to be, the more memory it's going to require, and the more delay it's going to introduce in the network. So keep this in mind, even though it kind of sounds cool, right, to have all that security functionality in a single box, which, by the way, you try to make sure it's not a single box of failure, single point of failure, all right? Even though it sounds cool to have all this functionality in one place, it's going to hit your performance pretty badly, right? So keep this in mind. Don't just enable everything blindly, because the end users, the applications, and, well, God forbid, your customers, your paying customers, they're going to feel the the effects of your awesome UTM device, and their application experience is going to suffer. Now, a special type of network monitoring device can also be considered a web application firewall. We've briefly mentioned about web applications firewalls in a previous video, and we said that a WAF, web application firewall, is just a dedicated firewall that is specifically trained and educated to look at attack signatures aimed at web applications. So we're looking for things such as cross-site scripting. We're looking for directory traversals. We're looking at SQL injection attacks. We're looking at pretty much anything that could be performed by a malicious user that is trying to exploit a input validation flaw in a web application. So it's still an application layer firewall. It still looks at the application layer payload. It's just that it's a bit more, let's say, picky about what type of traffic is it going to analyze. So it's only going to look at web traffic, and it's only going to look for web attacks, web application attacks. It's mostly going to rely on signatures. That's because we cannot really do much when it comes to requests coming in from our clients. Behavioral analysis doesn't really play well here, because most attacks, especially web application attacks, are just one single request, one single query with a malicious payload. So in many situations, it's gonna be either black or white, right? We're detecting an attempt at an intrusion, we're detecting an attack in that request or not. It's pretty much not gonna be much of a gray area with web application firewalls. And you could deploy a WAF as a separate device. It could be a physical box, it could be a virtual machine, it could be a functionality within a UTM device. Again, all-in-one wonders. But it can also be a part of the web server itself. So we have plugins. that install alongside the actual web server that is hosting the web application, such as plugins for the Apache web server, for the IIS web server on Windows Server, or for Nginx. So we're installing these plugins right there, and their purpose is to scan the traffic that's coming in from the clients before allowing that request to be processed by the web server. Having something such as a plugin that runs alongside the web server on the same machine, on the same box, opens us to the risk of either having that machine compromised by an attacker who this time doesn't target the web application, but targets the scanning engine, and can intentionally cause, for example, a denial of service, give it so much traffic to analyze that the web server running on the same machine is unable to actually respond to valid requests. So there you have it, that's the denial of service attack. Now, when it comes to actually monitoring the network traffic, we said that a solution would be to just simply mirror all the traffic and then look for specific attack patterns inside of that traffic. Now, that might not be always feasible because the amount of traffic entering a data center or the server farm that hosts an application might be huge, right? So in some situations, we might not be able to analyze the exact amount of traffic that goes in, but we might be able to generate a summary of that traffic and then analyze that summary for intrusion attempts. Now, this traffic summary is sometimes found under the terminology of NetFlow or SFlow or JFlow, which is basically just a technology implemented by various vendors out there, in which instead of creating an exact copy of the traffic, we're simply summarizing that traffic and then reporting that summary back to some analysis software. So we're only telling it what type of sources, what type of destinations have communicated, how many bytes were used, what type of protocols have been used, what type of flags have been set in that specific type of traffic. But we don't put the burden of sending the entire actual traffic and the entire payload to that analysis software. Now, this also means that we're losing application layer visibility. All right, since we're just summarizing the type of traffic or only describing the metadata about that traffic, we're losing everything that pertains to the application layer. But we're gaining a lot of performance, and we can also store this summary information long term for further analysis somewhere along the line in the future. Sometimes looking at traffic is simply not feasible. Maybe we cannot grab all the traffic that's running through the network. Maybe we don't have network devices smart enough to generate those summaries, those flow reports for us. So another solution would be to simply have a software monitoring solution, or so-called a network performance monitor, that queries periodically your networking devices, queries your routers, your switches, your wireless LAN controllers, your firewalls perhaps, about the status of their physical resources, status of their interfaces, how much traffic is going through their interfaces, what's the CPU load, what's the memory usage, what's the structure of the routing table, how does the ARP table look like, how is the DHCP traffic looking like, right? So any type of monitoring information that can be extracted out of these networking devices, which in turn can be correlated in order to figure out if we can see some anomalies in there. One such solution is, for example, SolarWinds NPM Network Performance Monitor, which is a dedicated solution for monitoring not just networking devices, but also servers and virtual machines about their health, right? How are their network interfaces looking like? How much load is there on their hardware resources or their hardware components? Are they generating any alerts? Do we have failed interfaces? Do we have failed processes? Do we have something that's failed links? Are we detecting errors or overloaded devices? Stuff like that. Now, this type of performance monitoring can be done over a variety of protocols. In most cases, the SNMP protocol is going to be used because it allows us to report a lot of the hardware counters and a lot of the interesting information that we want to gather and store long term. Also, we might be using WMI, such as Windows Management Instrumentation, and a couple of other protocols as well. And of course, we could enrich this collection by collecting logs from the monitored devices and appliances as well. And we could be collecting those logs over syslogs, so we need to configure the device to actually send those syslog messages, or at least a copy of them, to the monitoring device. Or we could rely on an agent, an additional piece of software installed on the server, on the virtual machine, that periodically reports back to us everything of interest regarding that specific host. And when talking about dedicated software designed, specifically designed to analyze a lot of information coming from the network, be it network traffic, network summaries such as NetFlow, logs, and any kind of application data, that solution is most likely going to be called a SIEM, a Security Information and Event Management. Now, the key word in a definition of SIEM is correlation. That is, it's not just a place where you just dump all that information in a huge database. It's a place that, as you dump that information, is going to look for patterns inside of it. It's going to try to correlate network traffic with logs or application data with NetFlow data in order to figure out if some anomalous behavior is detected in your network. So a SIEM solution, and by the way, these are pretty expensive solutions out there, are never designed to be just log storage, right? They're engines, smart engines based on machine learning that aim to detect patterns of intrusion by analyzing and correlating information found in multiple log files. And what's interesting about the implementation of SIEMs is that they're supposed to collect logs from your network devices, from your security devices, even from your workstations and your mobile devices perhaps. And they're able to understand and correlate all that information and normalize all that information, even if it comes from tens or hundreds of vendors or thousands of devices. And they're able to normalize that information and make it look the same so that in the end, it can look for patterns inside of it. And it also allows you to perform queries in a language quite similar to a regular SQL language and query all that information regardless of the fact that it actually came from tens of hundreds of different vendors. And since a SIEM without machine learning functionality is not a very useful SIEM, we could use that machine learning features to look at user behavior as well, because in the end, we're trying not to detect just, attack patterns, we're also trying to identify who is conducting them. And a great risk comes from insider threats. So if we are able to monitor what our users are doing, we're not talking here about just watching what websites they're visiting or taking frequent screenshots of their workstations. No, we're not doing that, but we're looking at the behavior that they're exhibiting whenever they're interacting with specific applications. And if the SIEM has such an ability, we call that ability user and entity behavior analysis. Don't think that we're only performing here a witch hunt against insider threats. Think about the fact that we might be able to detect abnormal behavior because a user account has been compromised by a hacker, and that hacker is now acting on behalf of that user. The user might have nothing to do with that abnormal behavior, might not even know about it, might not even be logged in at that specific point in time, but the attacker might be acting on behalf of that user. If we're able to detect that abnormal behavior, we might be able to detect the attack going on right then. And stepping just a bit into the realm of science fiction here, I know that some vendors will say, no, this is not science fiction, we're selling this, we've had huge success with this. Well, yes and no. I'm going to keep being a bit skeptical as to how efficient this approach is. What I'm talking here about is sentiment analysis or emotion AI. That is, analyzing user behavior in what content the user is actually creating, as in blog posts, social media postings. We're not talking here about actual, analyzing the contents of emails and chats, because that might, step into the privacy area, which we might not want to do that. But by analyzing publicly available information generated by those users, we might be able to detect disgruntled employees. We might be able to detect unsatisfied clients that might create some bad reputation for the company, perhaps even before they become so upset as to take action or malicious action against our company. Again, take this with a grain of salt and don't just think that if it sounds awesome on paper, it has to be awesome in real life. If it sounds too good to be true, then it probably is too good to be true. And finally, the last term here that I want you to know about is SOAR, Security Orchestration, Automation, and Response. That's a mouthful, I know. It's usually a functionality built into SIEM solutions, or it can be just a standalone solution. What it basically it tries to address is the problem of too much information, that is, being overwhelmed by too many alerts, too many security events, too many security incidents, too many incidents that we need to determine if they're security related or not. Basically, the hell of any IT department that deals solely with monitoring the network and the applications. And the idea behind this is that a SOAR solution is supposed to use some machine learning techniques in order to not just figure out which anomalous events are occurring in the network, but by analyzing those anomalous events, it's able to take some action against them. So it could, at some point, determine if an attack is going on, even if it happens in the middle of the night, and take action immediately by blocking some ports, by creating an access list, by temporarily disabling some user accounts that might have been compromised. So that's security orchestration, automation, and response. Just to be sure everybody is clear on this, especially for the exam, where does the SIEM get its information from? Where, first of all, it's going to get it from logs, right? Syslogs. That's going to be the main source of information. How do you collect logs? Well, you don't really collect them. You expect those devices to send those to you. So those devices need to be configured, be it networking devices, there might be servers, there might be virtual machines, whatever type of device you have. Just configure them to send your logs to a secondary destination. If the SIEM is not the primary one, just make sure they send a copy of those syslogs to the SIEM device as well. Next, the SIEM can also collect data by installing agents on specific systems. Now, of course, we might not be able to install agents on, let's say, routers or switches, apart from some recent devices that are running Docker containers, perhaps. But in most cases, SIEM agents are designed to be installed on Windows and Linux systems. Then they're running as background processes that periodically scan the system and report back to the SIEM the logs generated by the operating system, the running applications, the log generated by the applications actually running on that host, depending on how the agent is configured. The built-in listeners or collectors that you're seeing here on the slide refers to the fact that the SIEM is pre-configured or has plugins that allow it to understand what different vendors are reporting back to it. So it's going to have different plugins to understand logs coming in from Cisco devices, HP devices, Dell, VMware, whatever vendor it is. It needs some sort of a plugin to understand that specific log format, and more than that, it needs to understand the contents, the payload of what the log is saying. SNMP traps, again, most monitoring information is going to come in through an SNMP query or as an SNMP trap generated by the device back to the SIEM. And also NetFlow. NetFlow or different variants implemented by different vendors are basically just summaries of the traffic flows detected over a certain period of time, collected, and then sent over to the SIEM device in order for that traffic summary to be analyzed. Finally, the SIEM can also capture raw packet data if it has dedicated sensors that are able to generate a copy of the traffic and send it back to the SIEM, or we can even have sensors installed inside of a network that are monitoring real traffic, and they're only telling back to the SIEM or reporting back to the SIEM a summary of that traffic. This is very useful when your devices don't have enough reporting on monitoring capabilities to report back to the SIEM device, and instead you need to install some specific sensors that look at the traffic and then tell the SIEM the necessary information that it needs to perform those correlations. Sometimes a sensor such as this one might be an IPS or an IDS device even. Log normalization is a feature built into most SIEM solutions out there, and normalization is required, and it's a very important feature because the SIEM is designed to collect information from hundreds of vendors and thousands of different appliances, each of them running different operating systems on different versions, and they're all building syslogs and SNMP traps in different formats. Some are reporting them as text, some are generating logs in binary format, some logs are in JSON format, some are in XML format or CSV format, depending on how the vendor actually designed its logging and monitoring abilities. We might even find differences as to how the logs are actually encoded. Some of them might be using UTF, some of them might be using some regional encoding. We might even run into some issues due to the fact that the new line character is represented differently between Windows and Linux systems. And that also might be reflected in the payload included in the logs that we're receiving as part of the monitoring process. Not to mention the fact that the SNMP MIBs, basically the database schemas that each vendor is using for their own software solutions or hardware appliances, these are completely different, not just among vendors, but also among different products from the same vendor. So in order to have all this bunch of information collected in some centralized location and to be able to query all this information and to be able to approach it in a consistent manner, we need normalization. That is, taking all this information coming from so many vendors in so many formats and making that information look exactly the same so that it can be stored in a single database that can be queried at once, regardless of the source of that information. So what are we using to normalize all this information coming from all these vendors? Well, you guessed it. We're going to need some plugins. Some of these plugins come from the SIEM vendor itself. So they're going to be pre-packaged with vendor plugins for major vendors out there. Some of these plugins are going to come from the actual vendors. So if a smaller vendor creates some, let's say, smaller firewalls at some point, and they want to be able to integrate with large-scale SIEM solutions, they're going to provide you with a plugin for their own environment as well. And another type of normalization that is really, really important is timestamp normalization. Don't forget that we're looking for anomalies in network traffic and in network events. And if we don't have timestamp normalization, if we don't make sure that all the events that we're looking at are actually stored with their right timestamp at their right moment in time when they actually happened, we have no chance of detecting anomalies in the network. So we might have devices that have a badly configured clock. We might have devices that have been configured for different time zones. We might have devices that display time or timestamp those time values in their logs in one format versus another format. Some of them might be using 24 hours, some of them might be using 12 hours, some of them might include the daylight savings time, some of them might be using UTC or Unix epoch time. It's up to the vendor. So normalizing these timestamps is also a very, very important topic here that needs to be taken care of by the SIEM solution before that event indicated by that specific timestamp is stored in the database alongside with the others. Now, the way a SIEM solution can look for anomalies in that huge database that we just talked about, well, it could be done in a number of ways. We could just rely on simple if, then, else matches. So we're looking for, specific events, specific types of logs being generated in a specific time range, perhaps. This type of approach is the fastest one because it's basically boils down to a simple query in that huge database stored by the SIEM appliance. Unfortunately, if there are unknown threats, if there are attacks that we know nothing about, that we don't have a signature for them, we don't know what to look for, we're not going to be able to detect them. Kind of makes sense, right? So another approach would be heuristic rule matching. This is a type of rule matching where we're not exactly looking for an exact match for the specific type of event, but we're looking for something that it's pretty close to it, all right? So this type of approach relies on a more permissive set of rules. So if it doesn't 100% match our rule, let's say if we have some events that are pretty close to it and match it like, let's say 80 or 90%. Now this also requires you to fine-tune your rule set. So if at some point by doing heuristic rule matching, you're detecting some anomalies, but you don't have a rule that matches that anomaly 100%, well, you'd better create it, right? You'd better fine-tune your rule set and add some more rules or tweak the existing ones to match that newly detected anomaly. And just to recap this here, a behavioral analysis implemented in a SIEM relies on the fact that you need to build a baseline. You need to tell the SIEM, how does your normal look like? How does your normal traffic look like? How does your normal logs generated by all the devices and all the applications in your network looks like? So that in turn can be used as a starting point in order to detect potential, well, mismatches that might indicate attacks or attempts at compromising your network. Now, of course, this is going to create a lot of false positives. So you might run into a situation where an alert is being raised because an application starts generating some huge backups because some admin has modified the backup policy. Now, the SIEM device sees a lot of traffic in there, raises an alert, raises everyone from their sleep at 3 a.m. in the morning, and saying that, oh my God, this looks like a data exfiltration attempt. Somebody is dumping all the data from our database. And then an admin has to come in and intervene and say, my dear SIEM, what's happening in there, what you're seeing is just a full backup happening at 3 a.m. in the morning. It's okay, right? Don't freak out about it. Okay, so it does require human intervention for fine-tuning these rules. On the other hand, we have anomaly analysis, and this is by definition a type of analysis that is performed whenever we're comparing observed behavior with known standard behavior, especially when we're comparing what we're seeing as part of a protocol's behavior with what the SIEM device knows that the protocol is supposed to behave according to its RFC, according to its definition. Finally, with trend analysis, we're going to be looking at historic data and try to extrapolate it. For example, if we see that the backups are increasing every single week because more data and more data is generated, the SIEM device might be able to generate a pattern so that if we see 5 gigabytes in backup this week and 8 gigabytes of backups next week, when it is going to see 12 gigabytes 2 weeks from now, it's not going to raise an alert because it expected the backup volume to increase by that amount. But I don't need to tell you that not everything can be safely predicted this way. Finally, after all that advanced correlation and machine learning and AI features, the SIEMs actually can be used as a database for event storage, and they can be queried by human users, by admins, if you know what to look for. Perhaps you just need to investigate some event, perhaps you need to perform some forensic analysis. So those databases become available to you, to any admin basically, simply by creating specific rules in order to match specific types of events stored in there. So you could create simple rules that are matching based on specific conditions. Look for one specific IP address, or look for a specific time range, look for one specific string that might occur in all those log payloads. Maybe look for a user and see what are the events that are generated by that user or that implicate that user, and so on and so forth. So the SIEM appliances are going to allow you to create some queries very similar to what you might be already used to if you ever used SQL in the past, because all that data is basically stored in a relational database, which can be queried with an SQL-like language. And finally, don't forget that at the end of the day, not everybody has money to invest in a SIEM solution. So you might end up having to analyze your logs by yourself, just navigating a bunch of logs. And this is where a bunch of text matching utilities, especially some utilities that are built into most Linux distributions, are going to come in and help you tremendously. Now, this is not a Linux course, and the exam is not going to expect you to know everything about all these command line commands. But I would say that knowing at least the commands right here on the slide is going to help you figure out a couple of the outputs on the exam. All right, so without going into too much detail here, let's have a look in one of my folders here that stores log files and an Ubuntu distribution. This is running on WSL, right, Windows Subsystem for Linux. We have a log file right here, dpkg log, which is the log that's generated by the package managers. So this log is going to tell me which package-based operations have been conducted on this machine from its beginning, from its installation, right? What did I install? What did I uninstall? What did I upgrade? So it might be some useful information in here. So let's just see a couple of these commands. Cat is the concatenate command in Linux, and can also be used to list the contents of text files. So cat dpkg log is going to provide you a bunch of listing right here, trying to display all the contents of the text file right at the console. Now, this file right here, we could also pipe it. So resend the result of this cat command to another command, which could be word count. Word count minus L, this is going to count the lines in this log file. So you can see it's over 9,000 lines long. Pretty tough to search for some information in a 9,000 line log file. So what we can do right here is, for example, limit the amount of information that we're displaying on the screen. This is where the head or tail commands come in. The head command, as you can probably guess, is going to provide you with a listing of the first 10 lines in this log file. Similarly, the tail command is going to provide you a listing of the last 10 lines in the log file. The tail command is very useful for log files that get appended frequently. So you just want to see the last modifications made in this file, use the tail command. Of course, the number of lines is configurable. We're not going to go into all these parameters right now. If you're interested in finding out more about any Linux command, any Linux utility, just use the man pages, man tail, and it's going to provide you with the manual pages that are going to tell you what are all the possible configuration flags or settings that can be added to this command. Here's the -n, for example, number of lines. Output the last number of lines. You can add it as a -n parameter, or -- lines equals how many lines you want to display on the screen. Quit with the letter Q. Now, the grep utility is a regular expression evaluator, which can be, of course, used to run some complex regular expressions which are going to help you tremendously dig through a lot of information and extract what is actually useful to you. But we can also do some very simple string matching using grep. For example, if we are displaying the dpkg log here and piping this to the grep command and search for, let's say, installation of a specific package, such as, let me see, Ansible, right? I did use this machine for Ansible in the past. So there you go. These are all the log entries in here generated by the Ansible package. Notice that we've been through a number of Ansible versions in here, starting from version 2.8.1. We went through 2.9.19, 2.9.27, and so on. We can even see the evolution of this package on this machine. Now, this is just a very, very simple example here. Just wanted to let you know that you do have a lot of utilities available at your disposal for manual log searching if you don't have a SIEM solution available. All right. Now, there's a lot more to talk about this, but since this is not Linux training, we're going to stop right here. All right, everyone. Thanks so much for watching. I know there's been a lot of information in this video, but I hope you found this useful and informative. And I hope to see you on the next video as well. Don't forget to leave a comment if you like this. Support the channel if you can, if you wish, if you find this useful in your studies, and see you on the next video. Bye-bye.